Welcome to section 12.3, our final section that I will lecture on regarding counting principles. So remember that in sections 1 and 2, whenever we were determining the probability of an event, we had to count how many ways an outcome could occur. And then we made a fraction with that and the sample space. Well, sometimes counting can be a little tricky depending on what is the scenario we're given. And in this example, we're going to look at two counting principles. So here I have this little diagram drawn here. It's called the mouse maze, and it is also on page 637 of your book. 637. And there are two scenarios that we're going to talk about. One would be, first I want to say, here we have box X, box Y, and box Z. And between box X and box Y, there are 4 paths. And between box Y and Z, there are 3 paths. And if I put a mouse in box X, and I said to you, how many ways could this mouse go from box X to box Y and then box Z? Well, he could go the first way and then the first way, the top, or he could go the first way and then the second way, or he could go the first way and the third way, or he could go the second way and the first way, or the second way and the second way, or the second way and the third way, or he could go the third way and the first way, or the third way and the second way, or the third way and the third way, or he could go the fourth way, then the first way, or he could go the fourth way, then the second way, or he could go through the fourth way and then the third way. So in order to count all of those, we could just multiply. There are 4 ways this way, and then from box Y to box Z, there are 3 paths. And so that is, if I multiply the number of ways for the first event times the number of ways for the second event. In this case, it would be going from box X to box Y, and then box Y to box Z. It would be 3 times 4. There are 12 ways of doing that. A different scenario would be if we take the mouse and we start in box Y, and we say, how many ways could the mouse go from box Y to box X or box Z? Or, so box event A or B would be the sum, right? He could go this way, and that's 4, or he could go this way, and that's 3. So that would be the sum of these numbers. So there are 12 ways to go from X to Y, then Z, and there are 7 ways to go from Y to X or Z. Okay, so the key words here are then and the word or. When it's A, then B, you multiply them. And keep in mind this idea. Starting here, going A, then B, you multiply them. If it's A or B, then you're starting here and saying this or this, and you add them. This is all explained on pages 636 to 637 of your textbook. Please read that. And I'm going to take a look at odd questions on pages 639 over to number 15, I believe. Sorry, I have my notes here. I'm doing up to question number 15. So, 1 through 15, odd. Here we are. Okay. So, the first question is on page 639, and it asks us to work the following problems. So, number 1, wardrobe, clever, has 15 pairs of slacks and 23 shirts. In how many different ways could wardrobe select a slacks and a shirt combination? Okay, so is this A then B, or is this A or B? Now, he's not going to wear a shirt or slacks. He's wearing a shirt then slacks. So for number 1, we are going to think of the first one. And those numbers were Sorry, I forget already. 15, then 23. Which is 345. Okay, so we just have to kind of figure out which one is it. He picks out a pair of pants, then he picks out a shirt. He could pick out any of these 15 pairs of pants, and then any of the 23 pairs of shirts. And if you do, pant 1, then shirt 1, or pant 1, shirt 2, pant 1, shirt 3, you would come out with the product of 15 and 23. It was 345. Okay, let's look at number 2. Natalie Attired has sorry, that was number 2. I would like to do number 3, excuse me. A salesman has 7 customers in Denver and 13 customers in Reno. In how many different ways could he telephone A, a customer in Denver and then a customer in Reno? So that's multiply. B, a customer in Denver or a customer in Reno. So our numbers are 7 and 13, so we're going to multiply them here, and we're going to add them here. Okay, let me take care of these right here. Okay, let's look at number 5. 5 has a pizza establishment offers 12 kinds of meat toppings, pepperoni, sausage, etc., and 5 kinds of vegetable toppings, onions, green peppers, etc. In how many different ways could you select A, a meat topping or a vegetable topping, meat or veg, and B, a meat topping and a vegetable topping? Okay, so this is really just asking us to pay attention to, and or, right? If it's and, that's like this, then this is and. So that would be a multiplication, and or is addition. So for number 5, our numbers are 12 and 15. So we would multiply them, which is, I'm sorry, the or was first, excuse me. That's add them. Am I really getting these numbers wrong? 5. It was 12 and 5. 17. Excuse me. Sorry. I'm in dim light here, unfortunately. And B is multiplying them. 12 times 5. 60. That's 17 or 60. Okay. Looking at 7. A reading list contains 12 novels and 5 mysteries. In how many different ways could a student select a novel or a mystery? Novel or mystery. B, a novel, then a mystery. Novel, then mystery. That's like and. Or C, now this is different, a mystery and then another mystery. So it's mystery, then another mystery. Okay, and remember that we have 11 novels and we have 5 mysteries. So since it's or first, we're going to add those and get 16. Since it's a novel and a mystery, so pick a novel and then a mystery, that's going to be 11 times 5. So that's 55. Sorry, just checking my numbers here. Yep. But then now pay attention to this one. What happens if I pick a mystery? How many mysteries are remaining? So we're not even using the number for novels. We're only using the number for mysteries. So I'm going to do, there are 5 options to pick a mystery. But once I do that, I'm not going to sit there and read the same mystery again. That makes no sense. So that mystery is off the shelf now. So now there are 4 mysteries left. So that's 5 times 4. That's 20 ways in which I could pick mystery, then mystery. Okay, hopefully that makes sense. Because once I pick one, if I'm going to pick another one, there is 1 fewer on the shelf. Okay, so number 9. 9? Where's 9? The menu at Valerio's lists 7 kinds of salad, 11 entrees, so we have 7 salads. That's a 7. 11 entrees. That's the main part of the meal. Number 9. And 9 kinds of dessert. 9 dessert. This is supposed to be a 7. Now it is. Okay, so what do we have to do with this? How many different salad, entree, dessert meals could you select? And meals are considered to be different if just one thing is different. Okay, I'm just reading what that says. So we would want to find out then, what kind of example is this? Is this an or statement, or is this a this, then this? And usually when you order, you say I'd like this, then I'd like this, then I'd like this. So it is all 3 of these. So it's going to be 7 times 11 times 9. Multiply those out is 693. Okay. On to number 11, which is on page 639. Using only the letters in our favorite word we've ever heard ringing in our ears. We dream about this word. We talk to people at cocktail parties about this word. Logarithm. Out of only the letters in the word logarithm, how many ways could you pick a vowel or a consonant? A vowel or a consonant. Okay, well, I'm going to get rid of number 7 down here because it's in our way. Well, it is an or statement, so let's see. How many vowels are there and how many consonants? Here's a vowel, vowel, vowel. There's 3 vowels. And 1, 2, 3, 4, 5, 6 consonants. So that's a total of 9 letters. 1, 2, 3, 4, 5, 6, 7, 8. 9 letters. Okay, so a vowel or a consonant would be an or statement, so we'd add them. So it would be 9. Number 11b says, in how many ways could you pick a vowel and a consonant? So that's like the first one. We'd multiply them. 3 times 6, 18 ways is vowel and or then a consonant. And C, now this is a little interesting. How many different 3-letter words, such as ORL, HLG, AOI? Now you might go, but those aren't words. Okay, so they're calling them words, but they just mean how many ways can you combine 3 letters? So it's like 1, 2, 3 letters from the word logarithm. So we're not using, looks like we're no longer worried about, well, let me read the whole thing. Could you make, using each letter no more than once in any given word? There are 3 events. A, select the first letter. B, select the second letter. And C, select the third letter. So if I have 9 letters, remember I have 9 letters, how many ways could I pick a first letter? There are 9 there. I might just close my eyes and pick one. There are 9 possible ways. Then once I've put one there and I don't want to reuse any of those letters, then I only have 8 left. And then so I pick one, I have an option of 8. I close my eyes and pick one out and I put it in there. And now I close my eyes. How many are left? There are 7 left. Okay, and we're going to multiply these all together because it is like this letter, that letter, that letter. So it is the one follows the other. It's not or, it's then. So we're going to multiply these. 9 times 8 times 7 is 504. Okay, and that is all, I believe, for number 11. Yep, okay. And then we have number 13, which has sections A through F. So I will erase this. Hopefully this makes sense to everyone. And we'll move on to number 13. Again, remember, you can always rewind and replay, and you can always shoot me an email and ask me, you said something, didn't really make a lot of sense. Can you explain that again? And I will be happy to do that. Okay, so 13, we have A through F. Oh, I love when they do that. Give us a whole bunch of ones. A, B, C, D, E, F. Okay, let's see what we got here. 13A. There are 10 students in a class and 10 chairs numbered 1 through 10. That's to sort of differentiate each chair and say they're not, like you can't switch 2 chairs and it's the same outcome, right? So you have 10 students and 10 chairs. It's almost like saying there's 10 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chairs or what have you. Okay, so A, how many different ways could a student be selected to occupy chair number 1? All right, well, there's 10 students, and I just want to put somebody in the first place. So I'm like, I close my eyes and I point. There are 10 possible people I could have put there. Once I do that, after someone has been seated in chair number 1, how many different ways are there of seating someone in chair number 2? Well, how many people are standing there? There are 9 people standing there. So, in my first chair, I could put 10 people. In my second chair, one of them sitting down already, so there are only 9 people to choose from. So, there are 9 equally possible people that could go in that second seat. ... C. In how many different ways could chairs 1 and 2 be filled? Well, if in chair 1 there are 10 people, and chair 2 there are 9 people, and that's not an or statement, that's a one person, then the second person, I will multiply them. There are 90 ways to fill chairs 1 and 2. D. If chairs 1 and 2 are already occupied with 2 of the students, in how many ways could chair 3 be filled? Well, I occupied one here with one of the 10 people. Then one of the 9 people sat here. Then there's 8 people remaining. So there are 8 ways, or people. There are 8 ways I could fill chair 3. This is chair 1, 2, 3, and so on. E. In how many different ways could chairs 1, 2, and 3 be filled? So 1, then 2, then 3. Well, there's 10 people I could put in the first chair. Then there are 9 people I can put in the second chair. And then standing over there, there are 8 people left. So it'll take me 10 times 9 times 8 number of ways I can pick from the 10 people and seat them in the first 10 chairs. Sorry, the first 3 chairs, excuse me. So what is this? This is 90 times 8. That is 720 ways of doing this. Okay, and F. How many different ways could all 10 chairs be filled? Okay, now we're getting somewhere. Well, that kind of goes back to A, where I wrote out 10 of these, right? That would be, there's 10 people to put in the first seat. There's 9 people. Once I put somebody in the first seat, there's 9 people still standing over there. Now I pick a random one, I sit them, and any of those 9 could sit there, right? But now I pick one and put them down. Now there's only 8 people. And then, so I randomly pick somebody. There's 8 possibilities. I pick somebody and I put him down. Now there are 7 people. Then there are 6 people. Then there are 5 people. 4, 3, 2, 1 person left. So isn't that the same thing as 10? I mean, 10 factorial. Yes. 10 factorial. Okay, if you would like to evaluate that number, it's really big. And it is 3,628,000. Is that right? 628. Yep. I think that's what it says. 800 ways. I will tell you this. If you left this, I'd accept that, because this number is extremely large. Especially when you get into large factorials, it is okay to leave the factorial. But if you want to know the actual number, it's 3,628,800. Yeah. Okay, which is a lot. That's a lot of ways to take 10 people and seat them in 10 chairs. All right, I believe we have accomplished everything we are asked to do in number 13, and so I will now move on to number 15, which is at the top of page 641. Page 641, number 15. There it is. Many states use car license plates that have 6 characters. So 6 characters. 1, 2, 3, 4, 5, 6. Some of these states use 2 letters. and a number from 1 through 999. So that could be 6 letters. Okay, so letter, like letter, letter. Oh, let me do this. Letter, 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 and then number, number. Sorry, did I read this wrong? 2 letters. Then numbers 1 through 9,999. So this could be, AA0001, AA0002, and so on. Okay, and then could be BA0001, BA0002, and so on and so on and so on. And then CA, right? And then we can change A. This would be AB0001. So there's a lot of combinations here. Okay, sorry, I'm just trying to give you an idea of how big these numbers can be to count. Another possibility is to use 3 letters and then a number from 1 through 999. So I'm just going to take this out of here for a sec. So 1, 2, 3 letters, and then, so letter, 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 number, number, number. And it says the number is from, let's just read this carefully. It says the number is from 1 through 999, which means it could be like 001 or 002, or like, 997, 998, 999. So these digits could be from 0 to 9. That's actually 10 digits, right? Or 10 objects, I should say. 10 things that could go in here, because 0 through 9 is 10 things. Okay, so numbers would be, these numbers are from 0 to 9. And so letters, how many letters are there? There's 26 letters in the alphabet. And then 0 to 9 is 10 numbers that could go in here. So this would be 26 letters of the alphabet here. And then it says 999, right? So it could be 001. Ooh, we got to be careful. So this could be 10 things, and this could be 10 things. This can only be 9 things, right? There can't be a 0 here. Got to be careful here, right? There cannot be a 0 here if, oh wait. These cannot all be 0. That's why they wrote it this way. Okay, so I was not thinking of it that way when I first did this, but let's look at the question. A. Which of these 2 plans allows there to be more possible incompletes? How many more? Okay, so we do have to kind of figure this out. So it could be that we have, you know what, I'm going to do it this way. 26 times 26 times 9,999. I feel that's, I'm not sure we're counting for zeros here. We're going to multiply those out. This as a number. So 26 times 26 times 9,999. That does account for everything from 1 to 9,999. Yes, it does actually. It includes things that end in 0 and so on. So I'm not going to really look at it this way right now. But this is the number of letters, and this is the number of numbers from 1 to 9,999. Upon multiplying all of that out, we get 6,759,324. 6,759,324. The other way, we have 3 letters, so this would be 26 times 26 times 26 times 999. That's from 1 to 999. Well, if we multiply all of those out, we get 17,424. Okay, so clearly the second one is better. Or, not better, more choices. to do it that way. And I think it says by how much. I'm not sure I subtracted those, right? So 15A says, which is more possible? The second one, by how many more? How many more? Roughly 12 million. I don't have the answer here, sorry. You have to subtract these. Subtract these two numbers, so 6,759, 324 gives us okay, not 12, but 10,799,100, give or take. Okay, what about part B? Part B says, how many license plate could there be using either 2 letters and 4 digits or 3 letters and 3 digits? Well, here's 2 letters and 4 digits, and here's 3 letters and 3 digits, and it says how many could be using this or this. So, we'd say event A or event B. So it's A or B, right? So what should we do? We should add them. 6,759,324 or 17,558,424. Just checking to make sure those numbers are right. That's what I have. Yep. And when we add them together, because it said or, A or B, how doing this or this, is both of them added together is 24,317,748. Okay, sorry about the glare on there. All right, last but not least, C. What does C ask us? There are about 100 million motor vehicles in the United States. Wow. 100 million motor vehicles in the United States. Would it be possible to have a national license plate program using the scheme of Part B? Explain. Well, in Part B, it says that using either of those ways, we would get 24 million license plates that are different. And there are 100 million cars in the country. So you would not have enough license plates using this scenario of either 2 letters and 4 digits or 3 letters and 3 digits to license every car in the United States under a national system. And so that is possibly one reason why the states each do their own license. So whatever my license in New York State is, there could be a duplicate license in 50 other states, but mine's a New York plate, somebody else has a Massachusetts plate, a Connecticut plate, a Vermont plate, and so on. So they are actually different in that sense. That's another difference. So we would not be able to do this in on a federal level, on a national level, of having a license for each car if there are 100 million cars. And we can only, together with these two options, come up with 24 million license plates. I hope that makes sense. Okay, so we have looked at the ideas of probability and these two ideas of counting. Try to make sure these are clear, that you understand them. The homework will just be in section 3. It will be to do the even ones up to number 16. I will put this on the Skype. I hope those make sense, but we pretty much did the others, and also the Q questions. But we did all the other questions in sections 1 and 2 together. Okay, very good. I hope you all enjoy the rest of your break, and I look forward to seeing you again on, I think it's February 27th. God bless you all, and have a great time.